All right, hello everyone. In this video, I'm just going to briefly say a few things about some of the problems that I've worked out here. I've worked out some of the ones that people usually have troubles with, and just going to say a few things about them. For the step-by-step, of course, you can pause the video and check out my algebra steps that I've carried out. I'm just going to mention the big ideas here. So for the first one, which is question 5b, we have 9 to a power equal to 27 to a power, and we'd like to solve for x, and those x's are in those exponents. The idea that I'm using here is that if I can make these expressions both have the same base, then I can just let the powers be equal to each other. And I notice that 9 and 27 are both powers of 3. 9 is 3 squared and 27 is 3 cubed. So then I just take my 9 and replace it with 3 squared. I take my 27 in the equation and replace it with 3 cubed. So now I have 3 to a power on the left side, 3 to a power on the right side. I apply my exponent rules to simplify a little bit. And then now that I have two exponential expressions with the same base, I just let the powers be equal to each other and then solve for x. Since this is an exponential equation, I don't have to check my solutions. You certainly can, but remember, for logarithmic equations, you will have to check your solutions. That will be mandatory. But for an exponential equation, you can check your solutions or not. Okay. 6, we want to find the equation of g inverse here, and here g is a logarithmic function. Specifically, it's a natural logarithm. And remember, natural logarithm, that means we have a base of e. And that will come in handy in a few minutes. Because remember, when we're looking for the inverse of a function, so here the function is g of x, I first start out by, instead of saying g of x equals, writing it as y equals, and that's because y is just the, g of x is just the y values for that function. And then first thing we do is switch the x's and the y's. So we have, instead of y equals, x equals. Instead of natural log of x minus 1, it's natural log of y minus 1. And then we just have to solve for y. And solving for y is pretty straightforward. First thing we'll do is we isolate our natural log. So we want just the natural log by itself. So I divide both sides by -3. And then once I have this logarithmic function by itself, I'm going to take this equation and rewrite it as an exponential equation with base e, because base e, that's the base for the exponential function. That's the inverse of natural log. So e to the power of, and the input for e to the power of will be the same thing as the output for natural log. For the exponential function, the output, y minus 1, was the input of the natural log. Remember, inverses, they switch inputs and outputs. Once I'm at that point, it's easy enough to solve for y just by moving the -1 to the other side to become a positive 1. And now that I've solved for y, there we go, that's g inverse. For 7, we're looking first for the domain of this logarithmic function, and the key idea here is, of course, for a logarithm, they're only defined when the inside is positive. So this part, 2x over x minus 5, has to be greater than 0. So basically, we're now solving an inequality, looking for where is 2x over x minus 5 greater than 0. Remember that what we do is look for where is the numerator equal to 0, which happens to be at 0, so I put that on my number line. Then we look for where is the denominator equal to 0, and that happens to be when x is equal to 5, and so I put that on my number line. Then I take test points. I now have 3 intervals, things less than 0, things between 0 and 5, things larger than 5. So I take a test point in each interval. Here I took -1, here I took 1, here I took 6. And then I find out what is the value of this expression at each of those 3 test points. And I find that the values were 1/3 and in the first interval, so that means that we are positive in that first interval. -1/2 in the second interval, so that means you are negative in that interval. And lastly, we were 12 in the last interval, And so that means we were positive in the last interval. So where is this function, or where is the inside of this function greater than 0? Well, it's greater than 0 when we are in the less than 0 part of things, and it's also greater than 0 when we're in the larger than 5 part of things. So that's going to be my domain, and I just need to write it up, and there we go. I have it as f of x's domain is everything from negative infinity up to 0, not including the 0, together with everything from 5 onwards, not including the 5. We're not including the 0 and the 5 because, remember, we don't want the inside to be negative. We want it to be also not 0. It just has to be positive. Positive doesn't include 0, so that means we don't want to have the 2 points of 0 or 5 included. To find the next part, f of 6, so we put in 6 for x. That makes the inside 12. And so the exact answer, log base 3 of 12. To find the approximate answer, we use the change of base formula. And the change of base formula was that if you're looking for a log base a of b, that can be turned into natural log of b over natural log of a. That's the idea that I have here. So taking log base 3 of 12, I'll turn that into natural log of 12 divided by natural log of 3, and then just use your calculator to come up with about 2.619. So now solving some equations. This is 11, and for 11 there were 3 pretty tough equations to solve. The first one is a logarithmic one, and so I know automatically, because this is a logarithmic equation, I must check my solutions, because for a logarithmic equation there's always the possibility that your solution is extraneous. So first thing that I do is I'm applying my properties of logs. If you have 2 logs of the same base, and that's what I do, that are being added, that's the same thing as the log of the 2 insides multiplied. So instead of log base 6 of x plus 4 plus log base 6 of x plus 3, it's now log base 6 of x plus 4 times x plus 3. Next thing I just do to make my life easier is to rewrite this as an exponential equation. So instead of log base 6, it's 6 to the power of, and again we're switching inputs and outputs. Output was 1, so the input is 1. The output is x plus 4 times x plus 3, and that's because the input was x plus 4, x plus 3. And at that point we just have a nice little polynomial to solve, and you solve and you find your 2 values. I find -6 and I find -1. Now if you stop there, that's wrong, because you must check your solutions. And when I say check your solutions, check them using the original equation. So when I'm putting in values of -6 and -1, I'll be putting them in the left side of this equation and seeing, does it make the left side equal to the right side. So when I check x equals -1, everything works out just fine. I put in -1, I get log base 6 of 3 and log base 6 of 2. I use that log property that says 2 logs being added, you just multiply the inside. So that's where the log base 6 of 6 comes from. And of course, log base 6 of 6, one of the properties of logs, log base a of a is always equal to 1. In this case, the reason is 6 to the power of 1 is 6. Therefore, log base 6 of 6 must be 1. So left side and right side are equal to each other because the right side was 1, and there we go. Life is good. Now, if we try the same thing for x being -6, when I put in the -6 and simplify, I have log base 6 of -2 and log base 6 of -3, and neither of those are defined. So that's too bad for us. We stop right there. That means x being -6 has to be rejected. So even though we found 2 solutions, there's only one solution for this equation, which is just -1. The other solution was extraneous. For this one, we've got 2 to the power of and 7 to the power of, and 2 and 7, there's no way I can really easily write them as both the same base, or powers of the same base. So instead what I'll do is I take natural log of both sides of the equation. So natural log of the first expression and equal to natural log of the second. So remember here that what the reason I'm doing this is because one of the properties for logs is log of anything to a power, that the power can come down in front. And so that's the idea here, that when I take natural log of both sides, that allows me to bring those exponents down in front so that they're no longer exponents. Be careful here. The one caution is, of course, the x minus 1, when it comes down, put brackets around it, because the entire power needs to be multiplied by the by the natural log of 2. And then for the next stage, just taking that natural log of 2 and multiplying it by both parts. So we have x natural log of 2 and minus natural log of 2. I move people with x to one side, move everybody else to the other, factor out the x, and then to solve, I'll just divide by all of this business here. And then we wind up with an expression for x, natural log of 2 over natural log of 2 minus 3 natural log of 7. One thing that I just wanted to also mention here is this would have also worked just fine if you used any other log. So you could have used log base 10 if you wanted instead of natural log, and that means your answer would be in terms of log base 10s instead of natural logs, but actually those answers would both be equivalent. All right, next up. This equation is a really tricky one, actually, if you don't really look at it for a while and think about what you can try with it. You have here a couple of exponential parts that are both base 3, and there's no easy way to really combine them to get just one exponential expression. But then if you're looking at the powers, if I'm looking at the power on the first one, that 3 to the power of 2x, this is what gets me thinking, oh wait, hold on, that's the same thing as 3 to the power of x that's being squared. And that, of course, makes me think, is this maybe just some sort of disguised quadratic? And the answer is yes, it is. So the first term, 3 to the power of 2x, you could really turn that into 3 to the power of x that's being squared. And for 3 to the power of x plus 1, one of the properties of exponential functions is that you could say that that is 3 to the power of x times 3 to the power of 1, or I've written it as 3 to the power of 1 times 3 to the power of x. And so now you can see that we do have something where with a substitution it turns into something quadratic, because we've got a constant term, we have a something and the same something that's being squared. So there we go. We do a little substitution and say that u is equal to the 3 to the power of x. Substitute, and now we have a little quadratic to solve. It factors fairly nicely. We come up with two solutions, and then here we have to be a little bit careful when we're solving, because don't forget that we cannot just stop here and say, oh great, we found the values for u. We don't want to know the value for u, we want to know the value for x. So for u being equal to 1, I get to 3 to the power of x is equal to 1. And so now I have to think about what the answer to that question is. What power on 3 gives me 1? And I know 3 to the power of 0 is 1. So therefore my solution for that first part should be that x is 0. For the second one, we have 3 to the x is equal to negative 4. But one thing that we know is that for exponential functions, the output is always going to be something that's a positive number. Remember that the range for an exponential function is things that are larger than 0. And so here we're wondering, when is 3 to the x going to have an output that is negative 4? And the answer is never. So that means that there's no solution for this. And the other reason why you might realize that there's no solution, pretend that you didn't think about the range of the exponential function. If you tried to solve this by using a logarithm and you wrote 3 to the power of x is negative 4, therefore that log base 3 of negative 4 equals x, and that should be your warning, oh wait, hold on, that's undefined, so that means, again, no solution. So two really good reasons why 3 to the x equals negative 4 should be no solution. So that means, again, only one solution to this one, and just the value 0. Here's a nice little one. We've got the radioactive half-life sort of question. So this has a half-life of 43 years, and we take 10 grams of the substance. So first thing I begin with always is, what is my equation? And so here the amount at time t is my initial amount times e to the k times t. K is my growth constant, and T is my time being measured in whatever units I feel like using. So if I start off thinking about time being measured in weeks, then time is always going to need to be measured in weeks. Or if I think about time being measured in years, then for the rest of the question, time will be measured in years. So here we've got half-life of 43 years, and we take 10 grams of the substance. So 10 grams of the substance, that is your initial amount, A0. So A0 we know is 10. Now, the next thing that we know is that the half-life is 43 years, and a half-life of 43 years means that when time is 43, you'll have half the initial amount. And of course, if the initial amount was 10, then after those 43 years, you'll only have 5 grams left. So you know that then when time is 43, the amount is 5. And so that's what I've done. I've taken my equation and I've replaced that when time is 43, so we have a power of 43k on my exponential function. My initial amount was 10, and at that point after 43 years, the amount that I'll have will be 5. So now I have this equation, 5 equals 10 e to the 43k, and that allows me to solve for my growth constant k. And so just taking the usual steps, getting the exponential function isolated, then rewriting it as a logarithmic equation, then solving for k. And so once I've done all that, I've now rewritten my formula for amount of this substance at time t, putting in the value for k that I have. I'm not turning k into a decimal, I'm just leaving it as is, because I want to get the exact value when I come up with my answers for the next two problems. So the actual question in part A was wondering how much of the substance remains after 10 years, or in other words, what is A of 10? So I just put in 10 for T. And when I do that, and here I've put brackets in red because if you're putting this into your calculator, you'll enter 10 times e to the power of, and because you want this all to be combined together before it's put into the e to the power of function, you'll need to put brackets around it. So when I enter it in my calculator, 10 times e to the power of left bracket, natural log, left bracket, 1/2, right bracket, times 10, divide by 43, right bracket, equals. And then you'll get 8.51 or thereabouts. So about 8.51 grams of the substance will remain after the 10 years have passed, which makes sense. If the half-life is 43 years, then after only 10 years, you won't be very close to the halfway mark. So not a big surprise. That number seems reasonable to me. Next question, how long will it take for only 10% of the original amount to remain? And of course, if the original amount was 10, 10% of that would be just 1. So that's where I'm getting this first step here. We say that, well, we want the final amount to be 1, and we need to solve for time. How long will it take for that to happen? And nothing really fancy here. We're just now solving an exponential equation. I isolate the exponential function by dividing by 10. Then I rewrite it as a logarithmic equation. Then once I've done that, then I can solve for t and then run that through my calculator to find about 142.8. And so that's how long it'll take for only 10% of my original amount to remain. All right. Here we've got an angle and a right triangle. We're given a value for tangent. So what are the values of the other 5 trig functions? So first thing that we need to do is, of course, draw ourselves a little picture, and I've already drawn the triangle here. The other thing that we'll need to remember is that in right triangle trigonometry, tangent of theta is defined as the opposite over the adjacent. So that means that when I'm drawing my triangle, I know that for the angle theta that I've drawn here, that the opposite side must be 13 and the adjacent side to it must be 9. Once I've got that, then the one side that I need to solve for is my hypotenuse, and I use the fact that the two other sides squared when added together is equal to the hypotenuse squared, Pythagorean theorem, and then just solve away for my hypotenuse. When I take my square root, I'm taking the positive square root because, of course, we're talking about a triangle. Lengths have to be positive amounts, so that's why I'm not taking plus or minus square root. Don't forget, of course, that root of 250, you need to write that in simplest terms. Root of 250 is root of 25 times 10. 25, root of that is just 5, so we've got 5 root of 10. And so once we have these three things, opposite, adjacent, and hypotenuse, then we're ready to go. Sine is opposite over hypotenuse, 13 over 5 root of 10. Don't forget, of course, not to leave it in that form. It needs to be written in simplest terms, and that means rationalizing that denominator, multiplying top and bottom by root of 10. So on the bottom, you would have 5 times root of 10 times root of 10, which is same thing as 5 times 10, or 50. So there we go, we have sine, and while I'm here, I know that cosecant is the reciprocal of sine. So if sine is 13 over 5 root of 10, cosecant would be 5 root of 10 over 13. That's how I like to do these in pairs. And then I just do the same thing for cosine. Don't forget to write it in simplest terms. Use the fact that cosine and secant are reciprocals of each other. Then write tangent out, and then use the fact that tangent and cotangent are reciprocals of each other. And there we go. We've got the values of all 6 of our trig functions. Okay, a couple of calculations in 18. I want to find secant of negative 2 pi over 13. And my first move here is to turn this into secant of positive 2 pi over 13. And the reason I'm able to do that is because remember that secant is an even function. Secant being an even function means secant of negative theta is the same thing as secant of positive theta. So in this case, secant of negative pi over 3 is the same thing as secant of positive 2 pi over 3. So next move, I'm going to think about the fact that instead of finding secant, I'm going to say, well, instead I'll find cosine, because secant is just the reciprocal of cosine. So basically now my plan is find cosine of 2 pi over 3. I draw my angle 2 pi over 3, and that's in quadrant 2, reference angle pi over 3. So I know that I need to get my special triangle out. And for cosine of pi over 3, cosine of pi over 3 would be adjacent over hypotenuse. And adjacent over hypotenuse would be 1 over 2. So we have cosine of pi over 3 is a half. Now, next thing to think about is, of course, what quadrant are we in? And here our angle is in quadrant 2. And in quadrant 2, sine is positive, so is cosecant. But that means everybody else is negative. So that means next step for me to say is I know cos of pi over 3 is a half. But that means cos of 2 pi over 3, the angle that I was actually interested in, would have to be negative, so negative a half. And then I'm pretty much finished, because now that I know cosine of 2 pi over 3 is negative a half, then secant 2 pi over 3 needs to be the reciprocal of that, which is negative 2. All right. Let's do another one. Sine of 25 pi over 6, which if you were turning that into degrees, it's a fairly large angle. And so you know that you need to find a coterminal angle that's a little bit smaller than it. Remember that to do that, we're subtracting full circles. If you're working in degrees, I guess you'd be subtracting multiples of 360, but it's easy enough for me working in radians. I know that 25 pi over 6, I want to subtract a full circle from that, so I'm subtracting 2 pi, but 2 pi is the same thing as 12 pi over 6. So that's what really makes my calculation easy here. Really, I'm doing 25 pi over 6 minus 12 pi over 6, and that's where the 13 pi over 6 comes from. So we know that sine of 25 pi over 6 and sine of 13 pi over 6 are equal because they're coterminal. And I can get another full circle out of it. 13 pi over 6. Ooh, I lost the over 6 part. There we go. 13 pi over 6 minus 2 pi, that's pi over 6. 13 pi over 6 minus 2 pi is the same thing as 13 pi over 6 minus 12 pi over 6. So that leaves me just pi over 6 as my answer. So now, sine of 25 pi over 6, 13 pi over 6, and pi over 6, they're all equal to each other because those three angles are all coterminal. So now my plan is, let's find this. Let's find sine of pi over 6. And I've made my drawing. Pi over 6, we know what that is. That's basically 30 degrees in quadrant 1. So out comes my special triangle again for the 30, 60, 90 triangle. And for sine of pi over 6, sine is opposite over hypotenuse, and so we have 1 over 2. So sine of pi over 6 then is a half. And I know it's positive a half for my answer, of course, because we are in quadrant 1 where everybody is positive. Let's do one more. So here, cos of negative 7 pi. And so first thing that I do is, again, I'm using the fact that cosine is an even function. So cos of negative 7 pi is the same thing as cos of positive 7 pi. And then I'm just subtracting full circles. 7 pi minus 2 pi minus another 2 pi minus another 2 pi. All those angles are all coterminal to each other. So instead of finding cosine of negative 7 pi or positive 7 pi, instead I'm finding cosine of pi. Now, cosine of pi, or 180 degrees, that's not something that one of my special triangles will get me. That's where I need to think in terms of my unit circle. And remember, for angles in the unit circle, cosine of theta is the x value on that unit circle. And so here, for pi, or for 180 degrees, my x value is negative 1. So that means that I'm going to be taking then my value for cosine of theta being negative 1. And there we go. That's my answer for cosine of negative 7 pi, which is the same thing as cosine of pi, which is negative 1. All right, so here we've got an angle in quadrant 3, and sine of theta is negative 5/13. So if we're thinking about angles in standard position on the xy plane, we just need to first remember that sine of theta is y over r. So here I'm going to draw my angle, or I've already drawn my angle in quadrant 3. And I know that my y value has to be negative 5, since sine of theta is y over r. And remember what r is. R is the length from the origin to that point that I've picked. So r, because it's a length, is going to be a positive number. So that means that its y must be the negative number. That's how I know y is negative 5. Also, the fact that the quadrant that we're in this quadrant, quadrant 3, x values are negative here, y values are negative as well. That's your other thing to think about as to why is it negative 5 for y. Now, we just need to find the x value for that coordinate. And so we again use the fact that x squared plus y squared equals r squared. Putting in the negative 5 and squaring it, you get positive 25. Putting in the 13 for r and squaring it, you get 169. You have x squared is 144. And now when you come to take your square root, the question is it positive root or negative root? And again, go back to your picture and remind yourself that you're in quadrant 3. And so at this point, the x coordinate is negative, which means you must be looking at taking the negative square root. So x is negative root of 144, or negative 12. Now that we've got that, now that we have x, y, and r, now it's easy enough to put everybody together. And again, I do things in pairs. So starting with the fact that sine is y over r, or negative 5 over 13, and cosecant is the reciprocal of that, so negative 13 over 5. Cosine being x over r, and of course secant is the reciprocal of that. So cosine is negative 12 over 13, secant is negative 13 over 12. And then same thing for the last, tangent is y over x. In this case, y over x, negative 5 over negative 12 would become positive 5 over 12. And cotangent is the reciprocal of that, which is 12 over 5. One thing just to note here, just before I go on and say anything else, here, if you are noticing again that the quadrant that we're in, we should expect that because we're in quadrant 3, and that's the quadrant where tangent is positive and also cotangent. I should have the other four trig functions, sine, cosine, secant, cosecant, should be negative. And that's a nice little check for us to do. And lo and behold, there we go. We have all of these. Secant, cosecant, sine, and cosine are negative. Tangent and cotangent are positive as expected. If they weren't, then that would mean I made a mistake somewhere along the way. All right, I believe that's the last one, so this is where I will pause. And so there we go. Hopefully this has been helpful. And again, so you can pause the video to see the details of the algebra side of things. And there we go. Hopefully this was useful to you.